So let's continue with helicopters as our special type of vehicles. There's always some animosity between fixed-wing pilots and helicopter pilots for the communities on both sides. And one quote from the fixed-wing community about helicopters is that a helicopter is nothing more than a large collection of parts flying in close formation held together by grease and copper wire. And why is this? Well, when you sit in a helicopter, everything vibrates, everything shakes, and there are a lot of disadvantages actually of helicopters. They're noisy, less fuel efficient, and hence worse for the environment. More expensive as well, because they're technologically more complex. And so why would you want to fly a helicopter? Well, clearly, there are also advantages. The fact that you can do vertical takeoff and landing without the need for a runway and hover and remain in position outweigh all these disadvantages, and these two lists go to show that you should never just count disadvantages and advantages to make a decision, because otherwise you would never have had helicopters. And helicopters have been around for quite a while. In fact, they have been already in the pioneering years, around 30s, they were already experimenting, and they have stayed experimental for quite some time, because not even during the Second World War, they didn't really reach operational status in large numbers. It was really afterwards that we saw them. That Sikorsky was one of the pioneers who was able to achieve, to overcome the complex problems which you have when you fly a helicopter. And why is that? Well, one of the reasons is that everything is connected. If you look at the principle of a helicopter, we see the rotor having two functions. It provides both thrust and lift. And this makes a nasty connection between the vertical and the horizontal forces. And also an example of a complication is if we look at the power which is required, we see that the lifting power actually decreases when you increase the speed. But of course the propulsive power that's required, the yellow line here, increases. And that's because when you increase the speed of a helicopter, the rotor also starts to act as a wing and generates its lift without the need to bring it via the torque to the rotor. So you see that the required power, depending on speed, first decreases and then increases. So that's a very strange relation already for just looking at the overall perspective of the force equilibrium of a helicopter. But what's even more complex is how to control a helicopter, because there are many things to control. And let's have a look at these controls. I hope you can see it. There is a stick which is called the cyclic control, and this you can use to bank to control the attitude, and both in the longitudinal and in the lateral direction. It basically it's called cyclic control because you change the angle of attack of the rotor blade when it's on the right side. So for every rotor blade, this is something that cyclically happens. So you change the difference between the left and the right side, or the front and the aft side, for the angle of attack of the rotor blades. And in this way you can bank or pitch up with a helicopter. So that's the cyclic control with the stick. But there's also the collective control. It's a bit like a parking brake in a car. If you pull the collective control, you increase the angle of attack of the rotor blades collectively. That's why it's called the collective control. And on the same handle, the same lever, you will find the throttle, which is a twist grip, like a motorcycle, with which you can increase the amount of power that's being fed to the rotor by the engine. And then to control the heading of the helicopter and to counter the torque of the rotor, we also have the pedals here, the same position as where with a fixed wing aircraft you will find the rudder pedals, to control the amount of angle of attack of the tail rotor, so the amount of side force created by the tail rotor. So these are more controls than in a fixed wing aircraft, where the whole cyclic collective thing, of course, is absent. And this makes helicopters very hard to fly. And we have a video clip of a gentleman who is showing that helicopters are very hard to fly. He has not had flight lessons in a helicopter yet. Still, he has bought the helicopter already. And as men typically are, they don't want to wait until they finish the complete manual when they try something new that you've bought. And in his defense, I should say that he did not intend to fly the helicopter. He just wanted to see whether the helicopter was operational. So turn up the engine and see whether it functions. When you have acquired something this expensive, I can really understand that. Let's see what happens. So here it sits in the helicopter, the engine has already started. See the rotor turning. And of course, to see really whether the rotor works, just a few inches off the ground wouldn't hurt, right? Well, this is already more than he ever intended to fly, so he now decides to quickly land again. But it's not as easy as it looks. The cameraman taking cover. And this is then what's left over. In fact, he survived, I think, mostly unharmed. But his new helicopter didn't. And they may be hard to fly and hard to control. They're even harder to understand. Because if you look what happens with a helicopter, as soon as you gain speed, you get a bit of a problem with the difference between the left and the right side. On this side, the rotor is moving forward, and therefore the blade will get extra airspeed when we're moving forward with the helicopter. But on the other side, we reduce the efficiency of the rotor blade because it's moving away to the back side. So when you're flying, it's actually moving with the air. And this means that even a certain part, I'm trying to point at it here, so around the center, a certain part is even receiving the air from the wrong direction. It's like a wing that's being blown at from the other side. And you can see there's a huge difference between a lift generated on the left side and on the right side. So as soon as you go forward, you get a huge banking effect because one side of your rotor disc will become more efficient while the other will become way less efficient. And in a way, this was one of the stories with which you could initially explain why a helicopter would never fly. You could maybe fly vertically, but fly horizontally would be too complex and all the equilibrium of forces and moments would change all the time. But now try to imagine what to do about it. So if we want to change the angle of attack of the rotor differently with the cyclic, for instance, depending on where the rotor blade is during the rotation, because we can compensate this by decreasing the angle of attack on this side and increasing the angle of attack on this side. But of course the rotor blade that is on this side in one moment will, half a cycle later, will be on this side, and then it needs a different angle of attack. And that's technologically not an easy problem to solve, and which was one of the things why it took so long for the helicopter to become operational. But the solution to this problem is what is called the swash plate. And we've got a beautiful animation here which shows the principle of the swash plate. We see the yellow rods attached to the rotor blades, and they can control the angle of attack. Now when we move the complete swash plate up and down, we collectively change the angle of attack of the rotor blade, independent of the position of the rotor blades. And move it down again. So this is what happens when we pull the collective lever in the cockpit. But now if we start moving the cyclic as well, then we'll see that the angle of the swash plate changes. And this means that the yellow rods will, on one side of the rotor disc, will pull, and the other side they will push. And in this way, change the angle of attack of the rotor blade dependent on the position where the blade is during the cycle, which is exactly what we want. But imagine that there are huge forces on these rotor blades. So we have to make something that's able to transfer the control force, but that shouldn't create a lot of friction, and it should be able to resist the huge forces which we have on the rotor. Not an easy problem to solve, and technologically an extremely complex system, but also a very elegant invention. And this is only the main rotor. If we then look at the tail rotor is not just to control heading, but it also needs to counter the torque, indicated with Q here, that is fed into the rotor. Because if you pull the rotor in one side, of course the helicopter will try to move in the other side. And to counter this, we have the tail rotor to keep the helicopter from spinning. And this also means that if something happens to the tail rotor, your helicopter will start spinning out of control, and this is the cause of several crashes. And worst of all, it also means that if you change anything on the rotor, if you increase the thrust or you increase the collective, then you need to correct again with the tail rotor, because the amount of force, thrust created by the tail rotor also needs to adapt, and that's why it's also further out to counter this moment with not too much force. So you see the arm, the L of TR, indicating that you can then use a smaller tail rotor than the main rotor to counter the torque. But it creates another nasty interaction between the one side, in this case the symmetrical flight, and the asymmetrical flight. The risk of losing your tail rotor or breaking something has also caused people to look for alternatives, simpler alternatives, or to investigate whether we could do without a tail rotor. A number of alternatives have been invented. I can show a few. One of them is the NOTAR system, the first one here, and this is basically replacing the tail rotor with a jet stream. And this jet is even been operational. This NOTAR system has been operational on the McDonnell Douglas 600. Well, the torque is caused by the rotation of the rotor, but if you have a second rotor which rotates in the other direction, as we can see here on this Kamov helicopter, the same axis but rotating in two different directions, this also takes away the need for a tail rotor, as long as you make sure that the torque that's being fed to both rotors is identical, of course. And imagine also the swash plates of such a helicopter. That's way more complex to design, but it has been achieved by Kamov. And of course, to avoid many of the complexities of two rotors, you can also make sure that they're not in the same axis. And here we see the Chinook helicopter, the Boeing Chinook, and there both rotors are also rotating in the opposite direction, and this way taking away the need for a tail rotor. But there is even a fourth way, invented in the Faculty of Aerospace of the University of Technology in Delft by Professor van Holten, and this is called the ornithopter. And in this helicopter, this special helicopter, the rotor is flapping, similar to flapping wings, but then a flapping rotor, in this way creating the rotation, and this takes away the need to feed torque to the rotor, and therefore also takes away the need for a tail rotor. It's an unbelievable principle. You see an engine feeding energy to a rotor, it starts to rotate, but still you don't need a tail rotor. It seems to defy Newton's principles of action is reaction, but in fact it doesn't, because only energy is fed to the rotor disc. Well, if something happens to the tail rotor, of course you immediately have to make sure that you no longer feed torque to the main rotor disc. This means basically switching off your engine, or switching it to idle at least. And this means, of course, that you lose your main means of lift. And also if your engine fails, your main engine fails, the same happens, of course. Surprising thing is that with a helicopter you can still fly then. We already saw with the power requirements that when you move forward, a rotor disc can act as a wing. In fact, the gyrocopter vehicle uses this principle. It uses a rotor as a wing. And as long as you use your altitude to gain speed, you can use the rotor as a wing to fly. And then in the final part, what you can do is you can take out the energy of the rotor disc by reversing the flow of air through the rotor disc. So first, when the engine is still on, you fly like this. When you lose the engine, you quickly dive to maintain speed. And then in the final meters, you make sure that you use the energy that's stored in the rotor disc to make a safe landing. And this is the gliding of a helicopter, which is possible, and it's called auto-rotation, and is part of every training of a helicopter pilot. We have, in fact, of one of these lessons, these auto-rotation lessons, we have a video which you see the principle. Here you see the aircraft coming in, already quite low, so it's already increasing the angle of attack in the rotor. As we see, the rotor keeps spinning for quite some while. And now it gets really close. It's hard to see here because they're probably zooming out with the camera now. It has quite some horizontal speed, which you also need to lose. So just like a normal plane which you would flare, you do a nose-up maneuver to take out the energy of the rotor. And this doesn't look like a very violent landing. It's easy to survive, but not an easy maneuver to fly. So it's another reason why helicopter flying is hard. For auto-rotation, you need altitude and speed. And this means that if you don't have them, you don't have the energy, the kinetic and potential energy to perform an auto-rotation maneuver, you're actually flying very dangerously. And this is sometimes depicted by this diagram, which you can see that if a helicopter is taking off vertically, then initially it will have some, be very close to the ground, but very quickly it will not have a lot of altitude and also not a lot of speed. And this means that you're in this red zone, which is called the dead man's region or dead man's triangle of a helicopter. If you have sufficient amount of altitude, you will have plenty of energy, and in this case it ends at around 800 feet, as an indicator, so it's quite low. But you have to try to stay out of this dead man's region, and that's why it's preferably not to take off vertically with the helicopter if you don't have to. So with the helicopter, normally you would lift off only a little bit and then first gain speed, and then you, as indicated by the dashed line here, you avoid the dead man's region by first gaining speed and then gaining altitude. And the reverse is also true, so separate from the triangle, there's also this zone very close to the ground, where even though you have some energy in the form of speed, you will not be in time to react, and therefore that's also a very dangerous zone. So that's means that normally with a helicopter you fly a flight profile at an airport not that different from a normal aircraft, because you have to move horizontally as well, which also makes it easier for air traffic control at the airport, by the way. And also means that a trauma helicopter that lands somewhere downtown vertically and takes off vertically and takes a huge risk, which is worth to appreciate. Well, if you thought helicopters were complex, try this. The tilt rotor aircraft. They are both a helicopter and they can fly as a normal aircraft. Each of them is not that more complex than a helicopter or a fixed wing aircraft. But what makes these kind of aircraft very complex is the transition mode. And modeling that and making sure that the controls are right is very difficult. And it took an awful long time to develop it. Only since recently with the V-22, we see it in operational status. So that covers the part of helicopters, but there are more special vehicles. You will see them in the next clip.